velocity and speed measurements. The 3 input capture pins with multiple modes for pulse width and frequency measurements, and this has interrupt on change feature used for Hall sensor interface that we are going to see in coming section when we see how to control a BLDC motor using Hall sensors. Let us quickly see how a brushless DC motor can be controlled to a drive and what is the drive topology. Before moving on to this, let me give a brief introduction of brushless DC motor, how it is constructed, what are its features. A brushless DC motor is a synchronous motor that finds numerous applications in motion control. Appliances, automotives, aerospace, industrial automation are few industries to list. These come with different torque and voltage ratings. A brushless DC motor has windings on stator and alternate permanent magnets on the rotor. Brushless DC motors are electronically commutated based on the rotor position with respect to the stator windings. This means to run a brushless DC motor, an electronic drive is required. Normally, 3 Hall effect sensors are mounted on the stator that are used to determine the rotor position. The Hall effect sensors give a combination of high and low signals when they pass next to the rotor poles. With this combination of Hall effect sensor inputs, the commutation sequence can be determined, and we will see in a while how we can determine the commutation sequence and how we can control a brushless DC motor. A typical control circuit with the 3-phase winding connected is shown in this figure. Here, 3 phases, phase A, phase B, and phase C are connected to a 3-phase inverter bridge having the switches H1, H2, H3, and L1, L2, L3 are shown in this figure. H1, H2, H3 are connected to positive DC bus or power supply which is having positive direction, and L1, L2, L3 are connected to DC minus or the return path. Stator windings A, B, and C are connected in star fashion to this inverter. In coming slides, we will see how these stator windings are energized in synchronous with the Hall sensor input. This slide here shows what is the switching sequence that should be followed based on the Hall sensor input. With 3 Hall sensors on the motor, every 60 degrees of electrical cycle, a Hall sensor makes a transition either from low to high or high to low as seen here. Every 60 degrees, a Hall sensor makes a transition at this point, and the Hall sensor sequence changes from one to next. With this, every electrical cycle has 6 steps to complete one full cycle. That is 60 degrees per sequence, so 6 steps per 360 degrees of electrical cycle. The energizing sequence will have 6 combination of on and off of the 6 switches that we saw in the previous slide. A typical switching sequence is shown here. This table gives a typical example of switching sequence. The Hall sensor inputs are at 120 degrees phase shift to each other. If you see here, each of these Hall sensor makes makes a transition, and they are at 120 degrees to each other. So Hall A makes a transition here, and Hall B makes a transition from low to high at this point, which is at 120 degrees phase shift to Hall A, and Hall C makes a transition at 240 degrees with respect to Hall A and 120 degrees with respect to Hall B input. Every sequence has 2 windings connected across the power supply and 3rd winding left open. If you see the sequence, example of sequence here, every phase has 2 windings connected across the power supply and 3rd left open. Considering the first step where Hall sensor input is 1, 0, 1. Here Hall A is 1, Hall B is 0, and Hall C is 1. As it is seen here, Hall A is 1, Hall B is 0, and Hall C is 1. The switching sequence says that phase C should be connected to positive of DC bus, and phase B should be connected to negative of DC bus, and phase A should be left open. In order to achieve this, switches S3 and L2 should be on, or they should be connected or closed, and all other switches should be open or off. This will make the Hall sensor to this will turn the motor by 60 degrees electrical in a given direction. So by turning on S3 and L2, the rotor will rotate by 60 degrees, and this will make the Hall sensor to make another transition triggering the next point on the sequence table, and so on. So once these two phases are energized, the rotor will rotate by 60 degrees, and the next sequence will be hit by the Hall sensors. So this is the time. That is the time to energize the next winding. That is phase A and phase B, and phase C should be left open. So this should be continued to allow motor to run in one direction. But the electrical cycle and shaft rotation have a definite relation. The relation is the electrical cycle repeats every rotor pole pace. So to complete one rotation on the shaft, these 6 steps should be repeated as many times as rotor pole pace. In the sequence, if the sequence is followed with rated motor voltage across the motor windings, motor will run at rated speed. But the aim is to control the speed. So speed can be controlled using PWMs by PWMing each switch according to the speed required. This we will see in coming section how we can control the speed of a BLDC motor. The phase current waveform looks trapezoidal as seen here. It is in trapezoidal. It varies in trapezoidal with the 120 degree phase shift to each other. So phase A makes a transition here from 0 to high or low to high, and phase B makes a transition here, and they are at 120 degree phase shift to each other, and they are in trapezoidal. They are trapezoidal in shape. Let us see how we can interface a PIC18Fxxx31 to control a brushless DC motor. This slide shows the hardware interface used for controlling a brushless DC motor. PWM 0 to PWM 5 here. Control 6 power switches connected to make a 3-phase inverter bridge, as we have seen earlier. DC supply to the inverter bridge can be derived either from a DC power supply or power source,